It starts with a silence so deep you can almost hear the universe remembering. Something ancient flickers in the dark, light too early, galaxies too heavy, a cosmos that seems to be breaking its own rules. Maybe it isn't the data that's wrong. Maybe it's the story we've been telling about how all this began. The James Webb Space Telescope has done it again, caught the universe acting out of character. Somewhere in its deep infrared view, astronomers stumbled upon 6 massive galaxies that shouldn't even exist. They're calling them universe breakers, and the name fits. These things appeared just a few 100 million years after the Big Bang, back when the universe was barely 3% of its current age. And yet, each one is packed with tens to hundreds of billions of stars, galaxies that look as mature as our own Milky Way, showing up at a time when there should have been nothing but stardust and baby galaxies learning how to exist.
But we're finding masses in terms of stars that look more like the Milky Way or even a little bit higher. And so that was really a shocking finding. We didn't expect to find anything this big, this early.
Joel Leisure from Penn State said it best. We expected only to find tiny, young baby galaxies at this point in time. But we've discovered galaxies as mature as our own. His collaborator Erica Nelson didn't hold back either. It's bananas. These galaxies should not have had time to form. Their paper in Nature shows one of them might weigh in at about 100 billion suns. That's the kind of mass that's supposed to take billions of years to build, not a few cosmic heartbeats. If it's all confirmed, this discovery could blow a hole in how we think the universe came together. The standard story goes like this. After the Big Bang, everything stayed hot and chaotic for a long while before gravity slowly gathered gas into the first stars. But Webb's seeing something else. Giant, fully formed systems showing up too early, too fast, as if the universe skipped a few steps. Then came another shock. A different team studying a galaxy called JD's GS-Z13-1 found something even stranger. A clean, bright signal of hydrogen light, Lyman alpha emission, from just 330 million years after the Big Bang. That's supposed to be impossible. Back then, the universe was drowned in a fog of neutral hydrogen, thick enough to block all ultraviolet light. That haze should have blocked any ultraviolet light, including Lyman alpha, until roughly 1 billion years after the Big Bang, said Roberto Maiolino from Cambridge. Yet there it was, clear as day. Somehow, this young galaxy had carved out a massive bubble of ionized gas around itself. To make that happen, the first stars inside it must have been monsters, way bigger, hotter, and brighter than anything we see today. Or maybe, as another scientist suggested, there was already a supermassive black hole at its center, blazing so fiercely that it became one of the first active galactic nuclei ever formed. And just when you think it can't get weirder, another Webb team, led by Claudia Lagos in Australia, found that these early galaxies were breaking the universe's chemical rules too. Normally, a galaxy's mass, star formation rate, and metallicity, basically how many heavy elements it's made of, follow a predictable pattern. But 12 billion years back, that pattern collapsed. The most surprising discovery was that ancient galaxies produced far fewer heavy elements than we would have predicted, Lagos said. Even accounting for their age, their metallicity was about 4 times lower than expected. It was as if they were still drinking from the universe's original hydrogen reservoir, diluting themselves with untouched cosmic gas. Taken together, Webb's findings hinted at a universe maturing too soon, galaxies forming faster, light escaping sooner, chemistry bending its own rules. The more Webb looked, the more the universe seemed to slip out of its own script. And as astronomers wrestled with galaxies that grew too fast, light that escaped too early, and chemistry that broke its own code, another crack began to show. This time, not in distant stars, but in the very heartbeat of the cosmos itself. For decades, cosmologists had lived by a recipe that seemed unshakable, a 6-ingredient model called Lambda CDM. It said, dark energy drives the universe apart, dark matter holds it together, and everything else, the stars, the gas, the dust, makes up just a sliver of the pie. It worked beautifully. The cosmic microwave background matched it, supernovae distances lined up, and the grand architecture of galaxies seemed to follow its plan. Yet when they compared the early universe's heartbeat to the one we measure today, something was off. The present-day expansion rate, the so-called Hubble constant, simply refused to agree. One version painted a slower, calmer universe. The other said it's racing ahead faster than theory allows. At first, people thought it had to be a measurement issue. The galaxies were where Hubble said they were. The stars glowed just as bright. No hidden mistake to rescue the old model. So physicists turned to the only other possibility. Maybe the early universe itself played a trick. Maybe something happened back then, before the first atoms formed, that made the young cosmos expand just a little faster than we thought. A brief flash of hidden energy, a kind of cosmic cameo that sped things up and then vanished before it could leave a trace. If that were true, the ancient ruler scientists used to measure everything, the sound waves frozen in the early plasma, would be slightly smaller than we assumed. The math would stretch, and the present-day expansion rate would suddenly make sense. It's tempting, but hard to prove, though ideas keep circling: extra light particles, a fleeting pulse of dark energy, even a new kind of radiation. All the while, new observatories are closing in. DESI has already traced the large-scale skeleton of the cosmos and found it agrees with the slower expansion. Others, Euclid, Roman, the Simons Observatory, will soon peer deeper, cross-checking every assumption. If they side with the early universe, the standard model survives, just bruised. If they don't, something fundamental will have to give. Either way, cosmology is back at the drawing board, searching for the glitch or the new law that could make the numbers agree. Or maybe, once again, nature is trying to tell us it's stranger than we imagined. Because if the answer really is new physics, then somewhere in the first seconds of creation, the universe changed tempo. And we've only just started to hear the beat go off. Light, trapped for hundreds of thousands of years, finally escaped, stretching freely through space as the faint afterglow we now call the cosmic microwave background. Then came silence. No stars, no galaxies, just a vast dark ocean of hydrogen drifting under gravity's patient pull. That darkness didn't last forever. Slowly, gravity gathered enough matter for the first sparks to ignite, small galaxies, star clusters, and black holes feeding on whatever gas they could find. Their light began tearing through the hydrogen fog around them, stripping electrons from atoms and turning the universe transparent again. This was reionization, the moment the cosmos lit up for the first time. It didn't happen all at once. Instead, bubbles of ionized gas grew around these newborn sources, merging over hundreds of millions of years until the darkness was gone. We can still trace that story in faint clues scattered across the sky. When light from the most distant quasars passes through any remaining neutral hydrogen, it leaves deep shadows, what astronomers call the Gunn-Peterson trough. The cosmic microwave background, meanwhile, still carries the fingerprint of those first free electrons scattering photons as they reappeared. And the galaxies that leak out the right kind of ultraviolet light, the Lyman alpha glow, reveal where the universe's fog had already cleared. One day soon, telescopes tuned to the 21-centimeter wavelength will give us something even more powerful. A direct map of the universe's dawn, showing exactly how the first stars and black holes carved that fog apart. Right now, the evidence points to an army of faint, early galaxies doing most of the work. Tiny systems, each too dim to see individually, but countless enough to dominate the cosmic power grid. Their stars, possibly the first generation ever born, pure hydrogen and helium, no metals at all, would have been hotter, heavier, and more explosive than anything alive today. They poured radiation into the void, their light reshaping the entire intergalactic medium. A few black holes joined the effort, swallowing gas and spitting energy back out, helping clear the fog faster. And as those first galaxies and black holes lit the fog from within, another question began to flicker. Not how the universe cleared, but whether it had truly begun only once. That's why the search has become so precise. JWST is catching galaxies that existed only a few 100 million years after the Big Bang. Some barely held together, others massive beyond expectation.
Very, very rare in science that you make a big step forward in your measurement capability in the way that JWST has done for astronomy, and it just doesn't happen.
Ground-based arrays like LOFAR and HERA are hunting for the faint whisper of neutral hydrogen, trying to chart when and where the light broke through. Future instruments like SKA and Euclid will tighten every constraint, while the next generation of CMB measurements will refine the last remaining numbers. They all orbit one question: when the universe turned its lights back on, did it follow the script we wrote for it, or was it improvising? It was the first checkpoint, the first mirror held up to creation itself, showing us whether the cosmos we live in was born once or born again. And just when it seemed like the universe's story had looped neatly back to its own beginning, a Roger Penrose threw a match into the calm. He wasn't content with a single Big Bang. In his mind, our universe wasn't a one-time explosion, but one act in an infinite play, each cosmos expanding, fading, and handing its light to the next. And somewhere in that handoff, he believed, the ghosts of a previous universe might have left fingerprints. Back in 2018, Penrose and a small group of collaborators pointed to something strange in the cosmic microwave background. Faint, circular spots, just a little warmer than the space around them. They called them Hawking points, claiming they could be the dying echoes of black holes from a universe that existed before ours. According to Penrose's idea of conformal cyclic cosmology, when one universe grows cold and empty, black holes slowly evaporate, releasing their energy as radiation. As everything fades, mass becomes meaningless. The geometry of space stretches until time itself loses scale. And that radiation, squeezed through the boundary into the next cycle, would appear as tiny, hot scars in the newborn cosmos. His team said they'd found around 20 of these mysterious spots scattered across a third of the sky, each about 2 degrees wide. They ran simulations, thousands of them, and claimed none reproduced similar features by chance. To Penrose, they were echoes of eternity. To most others, just noise. The CMB, after all, is a chaotic sea of temperature fluctuations, quantum static, frozen into light. When you stare long enough at that chaos, patterns start to appear, the way faces form in clouds. Critics pointed out that Penrose's analysis didn't properly account for this look elsewhere effect, where random data can produce seemingly significant shapes if you search enough possibilities. Later studies, one led by Zhao and Scott, re-ran the same tests and found the supposed signal dropped to near statistical irrelevance, around an 87% chance of being just random variation. Others went further, using newer Planck and WMAP maps, machine learning tools, and stricter controls, and came up empty. What Penrose saw as relics of eternity, they saw as ordinary noise masquerading as mystery. Still, the idea lingers. Stubborn, poetic, impossible to fully kill. Because even if the data don't yet sing, the thought that our universe might have inherited the ashes of another remains irresistible. Maybe those patterns are real, or maybe they're the shapes we draw in the dark to feel less alone. For now, the sky holds its silence. Those faint circular patches, whether they're whispers from a previous universe or just mirages in the noise, hover like riddles we're not yet ready to solve.